you know? That purple is really...
Hello. Okay.
Do you guys know who gets donkey of the day?
Hello. You guys can hear me? Yes. Yeah, that's a yes. Oh, thank you. Okay. Hello. Happy welcome back to the week to physics. Okay, wait, I think we have a full house. I think we are recording. I think you can see, 1 second. Okay.
Whoa, what the hell is this? Is this Atlantis?
What? Atlantis? Wait, where's Atlantis? I don't see Atlantis. Should I see Atlantis? I see a lot of people in this class, which is good. I see like 35 people here. We're going to start a second.
Now I know what I was looking at when my friend was streaming Final Fantasy 14 one time.
I'm assuming that's not about me. Okay, we got a lot. All right. Awesome. Okay, so you guys know what you're talking about. Good. I don't. Fine. All right. I think we've got over 30 people here. We're
This
good
ain't
to go.
New York. This is the homeless people.
So.
Okay. You ever play Super Monkey Ball?
So right, I think everybody probably wants to mute at least for a moment. I think some people are having conversations in public they might not be wanting to have. I don't know. All right. All right. So I think we have a lot of physics to do today. I want to do like physics and tons of it. I don't particularly want to talk as much as I have been about grades or exams or anything like that. I just want to do the physics. A lot of you, so everybody, well, if you just, no books have been closed or anything yet. That is, I might still conceivably receive things on homework 1, and if I did, I would still grade them. So if you haven't turned in something, and as of last check, there were a couple people that you still really are encouraged to, you do want to, I think, and you could still get a 50 on homework, I mean, full credit. But everybody who did do homework 1, I do believe, unless they did it super recently, and I haven't looked again, I believe everybody's gotten their homework 1 back. I believe everybody got good scores. Homework 2, about half of you have gotten back. The other half of you have not. I apologize again. Hopefully, maybe by the end of this class, it might happen. But they're looking very, very good. I certainly looked at enough of the homework 2s to see how that was a lot of work for one night. That certainly was. Hopefully it wasn't too much work for a full weekend. Then there was also, oh, that was okay. Well, that was very nice of you to admit that, Justin. I had no idea it was you. Hopefully it wasn't too much work even with homework 3. Hopefully by the time you know, arguably homework 3 maybe should have, some years I assigned homework 3 before homework 2. I mean, content thereof. Like homework 3 is directly practicing the exact implication of what we got in class a couple days ago. Homework 2 is more like filling in all these dots and doing a blitzkrieg practice kind of thing to make sure we see the ins and outs of the math underneath, because we're going to need that in math in other ways the rest of the course, blah, blah, blah. So you know, it's 6 1, half dozen of the other, really, which one's easier for a person to do on their own first. But it does, I'm already over talking this. I'm just going to dive into homework 2 and start going over it. That's my point. We're going to spend maybe, we're going to go over all of homework 2, and maybe it'll take us all of today. I don't really want to spend all of today going over that one homework. Let me try to be as clear that this is possible. Every bit of that homework is real content that is not easy, that took me a long time to actually have a feel for. Every bit of that homework, even though most of it is technically calculus from calculus 1, which technically everybody was required to take, and we all know that. you'll see I will dribble out my philosophies on this calculus physics relationship more and more as the course goes on. But I love calculus, and I love it because of how I learned it through physics. I never loved it when I had to learn it for physics or when it was required or anything like that. And I certainly didn't love it until I started using it, blah, blah. So I am trying here in this course to teach my version of what we need out of the calculus for the physics. That means for some of you, it's a little repetitive right now, or a little bit drilling on things you're solid on. For some of you, I want to make it clear this is not supposed to be a reinforcement of what you never understood before, and it's supposed to be a new perspective and a clean slate to get calculus that you might not have gotten before. For all of you, I think it's very possible to think you get calculus and not actually get it, which just means it's very possible to master a lot of the operations, but never know when to introduce calculus or why or how to set it up. That's really what's necessary in physics. That's really what these homeworks are about. So all of that is to say, once I start this homework 2, you'll probably feel me seeming a little rushy because because a lot of what I'm saying will get repetitive. That does not mean the first time I say it, it's repetitive. You guys have to, in any calculus that is slightly becoming maybe clear now, that you're realizing was never clear before, you must ask about. You must not try to pretend that you always loved calculus or always understood it. There's no embarrassment in asking questions about things that you supposedly learned 2 years ago. The only thing I would caution you is, since it's very drilly and exercising this homework, when we start getting, like, please, we all pay attention. And when we start getting to the same thing over and over, then I'll ask you maybe to be careful and make sure we haven't already answered that question, and that maybe you just don't need to think about it for a bit. But like, we're going in here with a fresh attack on calculus. So we're going to go over homework 2, like starting momentarily. You're please going to ask tons of questions. You'll tell me if I'm dragging along too much, as I already am. You really will. I know you will. You'll tell me to speed up, but you'll tell me to slow down. Also, our major goal, it would be great to not have to worry about homework 2 anymore by the time this class is over. Ideally, even better than that, but ideally I'd like to get at least to homework 3 before this class is over, this whole class. So please help me with that. Last thing before I forget, as was mentioned in the homework, when you get to the end of these mathematical methods, the part that's like, a lot of it is about, the whole sheet is about what we're doing right now, about derivatives and stuff. But then at the end, all of a sudden it's about vectors, total departure. It like has nothing to do with anything we said thus far, but it's this vector stuff that we super deeply need very shortly. But the one thing I did say in the homework, I do want you to know that I made 3 videos about that. And I think it was based on that sheet last semester. So please, please, if I start rushing through the vector stuff, please on your own time, check out one of those videos. Okay. And I will take questions before I even start. I know I can't stand starting. I mean, I wish, anyway, or ending, or the middle. I just like the penultimate part. The one thing, on all the homeworks I've seen so far, all the homework 1s were great. Exactly what I wanted. Thank you. We're done. Homework 2 also saw great work, especially for something that everybody said was a lot. Whether you, I don't care whether you got it. I saw a lot of work and a lot of really thorough work. People did seem, anybody who handed in seemed to really get to the end, which is great. Just a couple of pointers for, please do circle your answers. I mean, there's a lot of things like this where it sounds kindergarten-ish, but every little contrived homework exercise is supposed to be a mini rehearsal for like publishing a paper or communicating to the outside world in some way. And for sure, nobody cares about anything but final findings. So you just make your final finding of every single question super boxed, highlighted, whatever, so I can see it from a mile away. And get in the habit of doing that, because I know in our hearts, we like doing that more when we're confident of the answer. And when we're not confident, we like to bury it. Get in the habit of unburying even wrong answers. It's better than not knowing where the answer is at all. I promise, I promise. So there's that. Spread out your work more. Everybody should spread out their work more. It's why I don't want you to write on the sheets. Like, like whatever your politics are in this class, we have to kill trees. I just don't know what to say about it beyond that. You must give yourself tons of blank paper space to write and think, like skip lines between questions. I personally do all my physics in art books, like in journals with online paper, not graph paper, because, and I save them because I want it to be beautiful while I'm going clear. I encourage that. But so spread out the work, circle the answers. Those were common things. And finally, substance-wise, I promise we're going to get to this now. I'm so bored already. Substance-wise, I think everybody was rocking it. I think people know what's going on with these derivatives and stuff. One thing to be careful though, once the e to the blah came in, once I was asking about like assume x equals some constant times e to the omega t, or even then e to the I omega t, I think people might have been a little bit fast and loose there. Watch the negative signs super carefully because the negative signs make a huge difference in this whole thing. So be alert when we get to that, or know that you might have felt confident, but negative signs really make a difference to the ultimate answer of whether something's a solution or not. So we'll look at that. Okay, I think I want to start. I'm going to start. Oh, I got to hook up. I'm going to hook up my whiteboard and pause to ask you. I haven't looked at the chat at all or anything while I'm hooking up this whiteboard. Can anybody, even if it's in the chat already, please ask any questions that I've, just any basics, like if I didn't get something back or so, any questions at all while I'm setting this up. I'm not looking, but I'm listening. Or if not, but no, everybody's good. It scares me when there's nothing. Oh, and I no longer have Zoom on my, is that possible? Is it possible to, okay. We're about to start. And by the way, someone gets I'm still tempted by Discord, but I know I'm not allowed, but someone gets a prize as we're proceeding. If anybody figures out from their perspective what it is I'm missing about setting up breakout rooms in Zoom, that's a prize right there for sure. I don't know what prize means. Okay. Okay. I'm going to start just because I've spent so long already. I'm going to start just with question one, and I want to back up and say, I'm going to remind everybody where we were last week, but I know it's too boring already. So first, I'm just going to start having you look at my work for the first couple of questions. Oh, unless it was all erased, that would be great. Can you see? I believe you can. Okay. I think what you're seeing on your screen right now is just, oh, for breakout rooms, thanks. I'm going to look at this chat while this is going. What you're seeing right now is me scrolling out just the beginning, the first couple of questions, just so you can see if you got the right answer or not. You can definitely stop me, but I'm going to look at the chat while this is happening. Oh, yeah, I appreciate that link. That was very nice. I've actually read that. It's actually less helpful than it sounds, but thank you. I do appreciate that link. It's one of those disciplines. All right. I'm going to just ask while this is scrolling. Again, right here, every homework that was handed in, everybody got this, right? It doesn't mean I've seen everyone yet, but this is almost just a straight up review of where we were. But what's happening, I'll tell you in this homework, just so you can see if you got there. I mean, what's happening here is we're trying to do exactly the same material we did in class, but we're doing it backwards, because the issue of differential equations is that it's like Jeopardy. With differential equations, you're really being given information that looks traditionally like some sort of answer, and you're trying to retrofit what you would traditionally think of as a question. And that starts throwing people off, or it's what makes it confusing, and particularly the grammar associated. So what's really happening is right now at the beginning of the homework, I'm giving you functions as though we just guessed them, and then we're testing them to see if they're right or wrong, right? Where it still doesn't tell anybody exactly how to come up with those guesses, but it's just showing you. All right, so this is the first question. I'm just gonna say, any questions on this so far? I mean, I know I'm doing this in a weird way, but like so far we're just checking what we did in class, that all right, the cosine function is a solution to the differential equation for simple harmonic motion. So yes, like that just confirms what we said in class. Actually though, let me pause and try to distinguish something about that. Yes, just to remind us. No, actually, I'm gonna go on. I'm gonna go until something's interesting. This is the next question. Please stop me. I know this is a weird way to teach, but just stop me if there's a question. I'm on question C now. It gave you a new function, here's what's going on here. It gives us a function, a sample function, that is a cosine function, that is written nice and generally the way we wrote it in class. And it's asking if it's a solution to, you know, our typical our one differential equation that we have so far in class. Let's start talking about why I'm making such a big deal of this differential equation. Like, it is one, it's one of many. It's the only one we have so far now. But what I'm trying to say is this differential equation we're focused on is the one for simple harmonic oscillation, i.e. anything that harmonically oscillates must be described by this equation, and anything that can be described by this equation must be an oscillator of some kind, even if it doesn't seem so at first, which is really the physics point. However, this question here, this 1C, what we're really just trying to drive in is, when I say harmonic oscillator, I mean a specific identified one. Like that blue writing, x equals a cosine, that is an oscillator. That is a solution to some oscillator. And then the blue writing down below, that is a differential equation that describes a harmonic oscillator. So one equation does have the proper form.
What's the temperature outside?
And someone please turn off mute if you like talking about the temperature or whatever.
The humidity.
I mean,
How does
please
humidity?
turn on mute, everybody. I guess I can do that.
In the water.
Like mute, like it shows that you, like mute. Hold on, let me see if I can just mute. I can't even. Oh, mute. Yes, I can. I have that power. Okay. And again, I keep your microphones off if you might at any moment say something about physics. I mean, keep your microphone on if you're going to say something physics, but if not, not. What I'm trying to just say right here is the blue equation in the middle of the page is a oh, can you not hear me? Can anybody hear me? Wait a minute. You can. Okay, thank you. So, all right. I'm going to assume that in general, okay. So, I just want to say that that blue equation is the differential equation for a simple harmonic oscillator, and the blue equation at the top of the page, a cosine, is what we call a solution to a harmonic oscillator, i.e., the one above does predict the motion as a function of time for some oscillator. Just the catch is that the one on top is not the oscillator that the one in the middle is talking about. The bottom line is they're two different oscillators. What do I mean? I mean they're oscillators with two different angular frequencies, like two rates of oscillation back and forth, which ultimately we found Wednesday means it's two oscillators made of different materials. Like there's two different omegas here, you know, and therefore two different square roots of k over m, so to speak. So the equation above is the type of equation that solves the equation in the middle, but it's the type, but the constants aren't right. So to solve a differential equation means you have to have the variables and the constants correct. I think I just got a question. Let me just pause for a second. And again, if I'm talking for, right. Yeah, so I mean, in other words, the solution, I'll just say it quickly. I'm not even sure if it asked, but that differential equation in the middle of the page, d2x, d22 equals negative 3x, like that is a differential equation. It is specifically a simple harmonic oscillator, but its solution would be x equals any constant you want times cosine of square root of 3t. I'm almost in, like, can I write this down? Like, yeah, not that it asked, not that the homework asked, but this means okay, and that we're going to see this over and over again, but so the answer is no. Since we are physicists, ultimately what we care about in an oscillator is both what it's made of and how it's moving through time and space. These are two different oscillators. Okay, is that a question? Right. This is just me dragging it out. I'm saying if you differentiate that solution twice, it doesn't check. The variable, you can make the substitution, everything in C. No, it doesn't check. We wanted something whose second derivative equaled -3 times the constant, but we got, -3 times the variable, but we got -25. So it's wrong. So no, again, just reinforcing what it means to be a solution to a differential equation. You can really only understand if you contrast it with what it means to not be a solution. All right, and again, stop me if there's questions, but we're going to the next one. Given another different oscillator, this time with an angular frequency of 5 radians per second, find its derivatives. All right, we're always finding 2 because that's the differential equation. And we get this -25a, oops, sorry, what I mean. Oh yeah. Yes, I'm getting a couple of good questions in the chat. One question is, can I say again what it means to be a solution? That is a fantastic question. That will be a fair question, even 50 more times. No, people could ask me that 13 more times over the next couple of classes, and I'll still think it's a valid question because it is the issue here. It's very funny phraseology. When I say, is something a solution, that's a very weird, like normally in math, you're used to getting a problem and being asked to solve it. I'm almost doing a weird like multiple choice thing here. I'm saying, here's a question. Now I'm going to propose an answer in advance and you tell me whether it's right or wrong. It's almost a true false thing. You tell me whether it's right or wrong. What does it mean to be a solution is the issue here. Like what it means for a function to be a solution means that if you take, specifically for it to be a solution to our differential equation, means that if you take 2 derivatives of it, if you take its second derivative, you get what our equation says you're supposed to get, which means you get the same thing back, but times a negative sign times a constant. Like literally, let me just say this one more time to everybody. If I ask, is blah a solution to the differential equation for harmonic oscillation, which is what we're talking about, that means I'm talking about some function of time, some single varied function of time. And I'm asking if you took 2 derivatives, one after another, of that function, would you get back what our differential equation says you're supposed to get back, which is negative times some constant times that thing itself, okay? I don't know if that'll become more clear, but this is, if that seems at all fuzzy to anybody, that's why I'm like drilling it with all these different versions of the same question. That's also just my apology to anybody who feels like they're being drilled. Like, I think it is a subtle question and you sort of see it over, but in any case, for any differential equation, what it ultimately means is like a function says a function is a rule that maps some dependent variable to some independent variable. A differential equation doesn't give you that information directly. It gives you information about the rate of change of the variable. So to be a solution means to be a function stated nicely and directly, to be a single valued expression that actually, once you take its derivatives, that it then yields whatever the differential equation says. It ultimately means that the 2 equations are consistent with each other. It still is a good question. I don't know if I helped whoever just asked, but I'll keep trying to say that as we go. So here, and in fact, as soon as we finish this one, I'm going to say more about that. But so here again, here we're testing solutions to see if they satisfy. But every single time, we're trying to see whether they satisfy. Oops, sorry.
مش عارفة أسعاره غالية أوي. 20 مصر جبت لي الصوت دقيقتين.
Every single time I ask this question about is it a solution or whatever, in this context right now, I'm asking, is something a solution to this particular differential equation, the one and only one we have in this class so far? We are going to have others, right? So that's why we're sort of trying to practice the whole concept right now. But right now, this is the one we're dealing with because this is just, this thing in green is Hooke's law written in mathematical general form. And that's what we're all obsessed with right now because we're going to build all of our waves and all of our transmissions and electrical fields and everything from little oscillators. Okay. I'm going to go. So here we tried one particular solution. We differentiated twice. We got back the expression at the bottom of the page. So what does that have to do with anything? Oh, sorry, it has nothing to do with it. I just did the instructions in the homework and got the answers. What I'm really trying to do in these homework problems, whoa, I don't know why that just happened. I don't know how that happened. Okay, really in this bit of the homework, I'm just trying to sort of show you how we keep swapping back and forth between omega squared and k over m. We're swapping back and forth because as long as because they're both measured in the same units, and as long as they are taken to mean two labels for unknown but unchanging numbers, then our cosine cosine proves to be a very good way to describe oscillators, and in the bargain we get this relationship between how fast they move and what they're made of. So I'm just trying to show that here, how omega and square root of k over m go back and forth. But then, and again, please stop me, I know I'm just, okay, then I think we get to part F, where now a little bit of something interesting and new we start to move into something a little bit new. Totally, somebody asked about this on Wednesday. I apologize, I forget who, but somebody completely raised this issue, and it's a great issue. And so what we're now, just trying a whole new function, like, because this is the point. All we've been doing is trying things to see if they work. There was no law that said we knew how to. There's no law that says that what we tried are the only things to try, but there is a law that says what it means to work, and that is to return yourself times a negative times a constant if you're differentiated twice. So we get this new function to try. It's another cosine. It's got the units correct, like it's got an omega in there, it's got an a, just like always. But here, they stuck another number in the argument, within the parentheses. They stuck in a 3.5. This is what somebody referred to on Wednesday as phi or phi. I mean, they used the Greek letter for it or some name for it, and it was correct, whatever they said. But again, all of these, we're not trying to assume that. Anyway, what's this 3.5 business? I don't know yet. Like, I don't know why someone just threw it in. I don't know why they want it. I don't know whether, I don't know what it's supposed to mean. But I can quickly start figuring out things about it the way I figured out any of this, like right from the get-go. Whatever 3.5 means or whatever significance it has, it must be measured in what units? Does anybody want to tell me? Like the 3.5, if this expression has any coherence, like I don't even care if it turns out to be a true or false, like working solution. If that expression means anything to anybody, then the units of 3.5 must be what? Kind of an unfair question. I'll say it again. Or should I do my obnoxious? Raise your hand if you hear me right now. Just electronically raise your hand if you're still with me. If I haven't. Also, I can see numbers go. Oh, this is like one of those games. Yes, not. It's like candy something. 14 parts. 15 people raising their. Oh, it's awesome. I don't even have to see. Okay, like half the class. Raise your hand if you hear me right now. Again, electronically. Right. This is like the wake up. If you 19, 20. This is good. If I were running for president, I would lose, but in an electronically fun way. 23. Okay, so. Half the class is, raise your hand if you're listening at all, please. 26, this is good. Please raise your hand or electronically indicate somehow if you are hearing me at all. Cool, 20, all right, 30. As soon as we get to 35, then I'm gonna ask my question again. Thank you, awesome. And right now, by the way, I'm trying to be polite, but this is not just an audio test. This is now a test to bring back the whole fold of physicists back with me into participation, because we got 25 people, and I wanna know from somebody what unit, given that we're looking at question F at the top of the, oh wow, I can't even do that. But we're looking at this question up here now. And we're looking specifically at this new idea of the 3.5. The question is, what units must that 3.5 be measured in? In what units must that 3.5 be measured, if anything makes any sense?
Is this what I was talking about in the last class? I was asking you a question. My physics constant isn't in the equation. Would that be the constant for this scenario?
Totally. And that's what I was just saying for 5 minutes. Yes, I was totally giving you full credit for that. Yes, this is exactly the thing you were talking. I couldn't remember that it was you, to be honest, but that's what I was saying. Yes, it is exactly the thing that you were talking about last class. This is that thing. So that's awesome. Right. We're finally getting to it now. But now maybe you or anybody could tell me what units, even if you didn't read anything, like obviously you did read something, but even if you didn't, just looking at the math expression, the 3.5 must be measured in what kind of units in order for anything to make sense here?
Radians?
Yes, thank you. And you were put on the spot by that, but yes. Okay, so you just added a year to my life. Hold on, let me just rearrange my state. I'm breathing freely now. Yes, the 3.5 must be in radians, like whatever it is, because it's in that parentheses, it's being added to something that's already measured in radians. Okay, so that's like that doesn't, I agree, it must be in radians. I'm just keeping that in the back of my mind. Now I'm gonna do the derivatives, right? Like we're being asked to. Oh yeah, and here, right, I think, now this is still, this is being dragged out for drama's sake, I guess, but, oh, someone's in the meeting. This, we're gonna just take the derivative twice, like we did everything else. We're just gonna check. In other words, this check is only real if it works when you don't have it should work on anything new, whether you've thought about it or not, right? So we're differentiating, we're losing internet connection, yeah, okay. We're gonna differentiate twice to see if it's solution, and we're just doing the same rules as before, trigonometric derivatives, and chain rule. By the way, if you had your hand up, please put it down now. I totally appreciate it, but you can put your, so nothing new in the math. If you know how to take a chain rule or a trigonometric derivative, still the same thing. It almost seems like it's a trick. It's just trying to jolt you into realizing that when you do chain rule to the part inside the cosine, right, the derivative of that whole business inside the cosine is still just omega as it ever was before, because it's technically the derivative of omega t plus the derivative of the number 3.5, and that's a constant. The derivative of it is 0. I'm over explaining as usual, but like I'm saying that when you take the derivative, you just pull that omega outside like we always did, and then you pull it outside again. So now where there's an interesting realization here is, okay, this is a whole different function, and this function right from the get-go, its derivative looked like something. This derivative of this function looks different from the old derivative. Like there's a 3.5 sitting in there. So something different's happening. But just like our old function, when we take the derivative twice, the whole key here is just like if the 3.5 were not there. And again, this was, I think I hate this point. Just like if the 3.5 weren't there, just like if, my gosh, okay. Hello. Oh yeah, it's going slow again for drama, but I'm doing it slowly like this just to force me not to go too fast, I guess. But what it's ultimately going to write is that just like before, if x stands for that whole expression, including the 3.5, then when we take two derivatives, nothing corrupted that expression. The expression is still sitting there intact, just as though the 3.5 weren't part of it. So it appears what we're saying here is, oh, even if you throw something in, again, I'll hit this point, even if you throw something into the parentheses, you're not going to change the fact that a second derivative of this will still spit back this. And that means that this too is a solution to our original differential equation. It's a gentle wake-up call, like, oh, just because you find a solution doesn't mean it's the only one or the most general one. It means you found something. Here we found something more general than before. We found that you can throw in a number there in the parentheses, and we've just been tacitly throwing in the number 0 all the while, whether or not we realized it. You're allowed to have a number in there in the parentheses, is what this math says, okay? The math says that there's a more general way to solve this differential equation than we might have considered. Of course, I wouldn't care if it didn't somehow connect us back to physics. So, all right, so we're just summarizing here at the bottom. Chat, look at chat. Oh, not, okay. All right, so yes. So this thing is going to be called, from here on in, this term that we're now we really do care about, and it's not even just a detail. This term is going to be called, we're going to call it the phase constant, or the phase. Tell me if you see this new screen. I'm not going to, where is it? Right, so even if you throw in a number like 3.5, your expression is still a solution to the differential equation for simple harmonic oscillation, yes. So from now on, we're going to say, anytime in the past 2 days we were saying, oh, if you're thinking of an oscillator, think A cosine omega t, or something like that, or x naught cosine omega t. We're going to say from now on, think cosine omega t plus some constant that we're going to designate with the lowercase Greek letter phi, or phi, nobody actually knows. I mean, you'd think it would rhyme with pi, but I don't know. It's not a spoken language, whatever. That letter, phi or phi, is going to stand for some amount of radians that can be thrown into your original expression. That's going to signify something physical, but that may or may not be zero. Either way will work. That's what we're establishing here. And in fact, let's pause for a second, I think. Yeah, more generally now, I'm saying, let's just back up. Like, why am I caring about what's the deal with all this math? The math takes a specific physical situation and blows it up to a general result that applies throughout the universe. So far, what we seem to have is, if I ever am walking through the universe, if I'm doing, like, if I'm collecting any data of any kind, despite what I'm looking for, if I stumble across something that's changing in time, some measurable. So if I come across anything any measurable quantity that seems to be changing in time, right? So a variable, specifically a dependent variable. If there's any quantity that I'm measuring, and it could be mechanical, like the distance of a spring from, the distance from the end of a spring to some position that we've measured. Or, so far as this math is concerned, I don't know that Z has to refer necessarily to anything mechanical. Z is a variable that could maybe refer to temperature, as homework 3 was trying to suggest. It could refer to color, if all of color can be put on some sort of numerical scale, which it can. Z could refer to some amount of, it could refer to a linear position, like a mass on a spring, or maybe it refers to the position of something swooping in an arc, like a pendulum. As long as Z is a dependent variable for which it seems to be the case that its second time derivative obeys this, as long as you have some variable, some measurable that's varying in time this way, then we say automatically that means Z, the value of Z, is oscillating harmonically in time. It's not only going back and forth necessarily, like some cosine-ish thing, but it's doing so harmonically, i.e. necessarily anything that can be described by this, any variable that can be described in this fashion, can be written as a cosine function of time, right? In the most general fashion this way, like with some constant before it, referring to what its initial value is, some constant before the time to make sure that we relate properly between cycles, whatever they might be, and the 2 pi that consists of every circle, right? That's what the omega is. And then this extra constant that we've just developed now, this thing called phi at the end, to express what? Well, you know this from regular cosines and sines, like that extra bit, that phase thing there, what that's like. New page. Sorry. I'm saying now, so we're now going to analyze what that phi is all about, because we really need it. I'm saying, I'm saying that little phi, which you even could call phi naught if you like, that phi that's stuck in the parentheses is serving a purpose like the x naught in, the equation of motion for free fall or for constant acceleration that you knew from physics 1. That is to say, x naught clearly is measured in meters. So in this old kinematics equation, I'm saying x naught is clearly measured in meters. Maybe it's not clear, but x naught is measured in meters, because the whole answer has to be measured in meters, and the whole answer is a sum of meters plus meters plus meters. X naught is in meters. What does it refer to? Well, it refers to the position measured in meters where the particle being discussed was at t equals 0, right? I mean, everybody knows this, but X naught was an initial condition. It was specifically initial position. That's what it meant. And specifically, that meant that X naught, by definition, meant the value of X when t was 0. Now, the reason I'm talking about it is because you usually don't care about that X naught. Like the minute you get used to physics at all, 99 problems out of 100, you drop that term. People don't care about it because they just, hopefully explicitly, but maybe even unconsciously in their mind, they're approaching every problem saying, oh, X naught stands for where something starts, like the first place it was when the whole experiment started, i.e. when I started paying attention. So where it starts means relative to some position that someone's calling 0. Well, that's relative. Like, it doesn't mean where the object starts relative to the Garden of Eden or the center of the universe. It just means relative to whatever we designate as 0. So the most convenient thing people always do is say, oh, I know, wherever the damn thing was when the experiment started, I'm going to call that 0, for heaven's sake. Of course, that's the right physics thing to do. People tend to say, look, X naught, it means the initial position. Whatever that is, let's just call it 0, right? And people do that and then drop the term and do all the physics. And that's what you should do, and that's right. And that's why you don't think about it much. But there's, now here, something similar is happening. The phi term is an initial position of sorts, but not in meters, of course. Phi is not measured in meters, it's measured in radians. So what phi means is it's an initial spot in terms of the cycle. It's an initial position with regard to the cycle. Your initial position could, for example, be 0. That would mean you're at the beginning of your cycle. Or if we said your initial position was like pi over 2 radians, or even better, pi radians, that would mean you're halfway into the cycle already when you start. You're right? Like phi naught, I'm saying, or phi, excuse me, and then we'll be done in a second. I'm saying something, as usual, I'm trying to say something both obvious and not, I guess. I'm saying that phi means initial position regarding so it's your initial place in the cycle, you could say, like whether you have a head start or a what do you call it, or delay. If you're starting right on point at the beginning of the cycle, or you're starting halfway into the cycle, or whatever, that's what your phi is. Just like X naught, of course, a cycle is a cycle. A cycle is a cycle. A cycle goes all around and on, and we start paying attention to a cycle whenever we want, and we call wherever we're paying attention, we call that 0. So what's the use of this term? Is a very good question. Like, there's a reason we got away with not caring about it for 2 days. Why should I care about it at all if I could always set it to 0? And I'm not really asking, I'm saying this term here is exactly like X naught in that whenever you can just set it to 0, sure you do. And you'd always do the simplest thing you can get away with, and then you drop it. But there's one scenario that's deeply important to this class that actually is the rest of the class. There's one scenario where you can't get away with just setting an initial position to 0, whether it be in the old equation or this one. I'm actually going to ask you to think about that for a second. I'm saying there's one circumstance, one type of circumstance, one type of situation that necessitates something like an X naught in the case of kinematics, or a phi or phi naught in the case of us. One time, I will always call wherever whatever I'm looking at, wherever it started at the beginning of the experiment, I'm going to call that place 0 if and when I can get away with it. But the one time I can't get away with it, should I say, or just, oh, just 2 people have a question? Is that, or does anybody, I'm not going to stop everybody, but if you have a thought on this or a question about it, just look at the chat. What I'm asking, I'll say it one more time. When do we actually need to designate an initial non-zero position, like in life? you'll agree when you hear it. You might call it a trick question. Oh, and my computer's freezing anyway. Oh, wait, just raise your hand if you can hear me, because actually I'm getting the red circle going on. Can you hear me at all? Oh, you can't hear me. Can anybody hear me?
I hear you.
Oh, you can't. Okay, you can't. Okay. All right. All right. I'm having. Oh, you can. Great. I mean, I'm definitely on a very slow internet connection. Well, I'll get. What I'm asking about, what I'm getting at, is why we care about this phase constant, and we do. And the fundamental reason is this: you care about. Oh, 4 people are raising their hand. Is that a question? If you want to say, please. Just someone shout out. If someone thinks they have an answer to this, please do. Or a question. You can. Oh, you can hear me. Okay. Okay. We need a phase constant because no one ever said there was only going to be one oscillator in our life. This is the point. Like in old physics, if you do x equals 1 f at squared plus x naught, you can, x equals 1 f at squared plus v naught t plus x naught, you can always just say x naught is 0 for some object. But if you have 2 objects or 3 or 4 or 5 involved in the problem, and they're starting at different places, then sure, one of them you can say it started at 0, but necessarily if 2 or more objects are starting at different places, then they can't both be starting at 0. It's just that straightforward, right? So somehow you have to keep track of where things are started when there's more than one object. If there's no meaning to a cycle at all. A cycle is whatever the heck you want it to be until you set multiple oscillators into motion, which we totally must do in this class, in our minds, in nature. It's coming up. All the phenomena we're looking at are actually require a collection of oscillators doing something clever with one another. So we need at all times to be able to track where one oscillator is in a cycle relative to another. And that's the bottom line of why we need this phi. I'm going to go just so, okay, and that's how we're going to use it. And maybe you already, hey, he said we need that. Yeah, okay. The question. Yes and no. I'm saying we need phase constant because we analyze multiple oscillators moving simultaneously. Let me even say that again, even more strongly. We are going to necessarily analyze multiple oscillators moving simultaneously. Specifically, however, I mean multiple identical oscillators. That's why it's an interesting question. It's a great question from Ayeta. But actually, I'm not like, the phase constant doesn't actually come in because of differences between springs or something. It comes in most powerfully if you have 100 springs made of exactly the same material, and therefore all having the same spring constant. And they're all prepared to oscillate in the same way, back and forth with the same period frequency and angular frequency. Still, you could set them to start at different moments. And if you do that intelligently enough, then what you start making is a wave ripple. And that's what we're doing here. So the phase constant tracks differences in cycle starts between multiple identical oscillators. Okay, so that is a great question. Okay. All right, so I think I'm just going to go on in the homework, I think. Back to, now we get to the, I'm just pausing it. Just remember one thing before I get to this next. Well, no, let's go on. Okay, so the next part in the homework, I mean, you can stop me with questions, but the next part in the homework says, it introduces now an exponential function. Still has omega sitting there. It's got t. It's got a negative sign there because, negative sign seems to, it doesn't seem outrageous to throw a negative sign in something we're guessing, but someone's just now guessing an exponential function and asking, and person who wrote the homework, me, is throwing out some kind of new function that we haven't talked about yet, and then asking us to take a couple of derivatives. No surprise, because we're ultimately going to check to see if it fits our second order differential equation, if it does or does not. Now, the reason I would even bring in exponentials or guess them is because we just realized that our cosine answer is one of a number of answers. Like our cosine answer was an example of something that works. We just realized a more broad set of things can work. In fact, In fact, with all this talk about the phase constant, you might have noticed, like if I'm saying over and over again that a solution looks like this, now I'm saying a solution to, if I'm saying this now over and over, or I could also write it like this, right? Or again, I want to emphasize, it doesn't even matter what the freaking variable is. It could be Z, it could be anything. But if I'm saying something like this solves something like this, then you know the only different phase, this phase constant that we introduce is like where a cycle starts. It's like the difference between this graph versus, I don't know, this graph or something. It's just where you start in something cyclical. So actually, of course, you all know if you take a cosine function and you shift it over by the right amount, like by pi over 2 radians, you still have a cosine graph that's just shifted over, but you could also call it a sine graph, right? In other words, and some people were submitting this right from the get-go on homework 1. In other words, everything I've been saying about cosines being a solution would also work for sines. I just feel like they're not as convenient. I'd have to tweak the constants more with sines because it doesn't feel like our system starts at the place that a sine thing starts. But what we're saying now is where it starts doesn't even change the mathematics. Like you could throw that in and address it with some constant. So really, what we're saying so far is if you have, if you have a differential equation, the one we have that looks like this. Oh, sorry. If you find that something behaves like this, where Z is any dependent variable and omega is any constant, right? So omega squared is any constant. So omega squared, I could have even just called Fred or beta or something, but I'm calling it squared with Monday morning quarterback thinking process. But if I had something like this, what we're really saying so far is actually, like anything, like something like, this could, any combination of cosines and sines, it seems like should work because we're already saying like a cosine and a sine are only distinguished from each other by a phase constant. And we've said now it doesn't matter what the phase constant is. It doesn't. So actually, so far what we're saying is in general, the kind of function that helps is some kind of cosine or sine, but I wouldn't have guessed tangent. Okay, hang with, all right, everybody just hang for, I'm going to finish the thought and then try to circle back. It's all I'm saying so far is this is what the physics says. This must be true. The physics says this thing in squiggly lines must be true about a variable we were originally calling X, but it shouldn't matter what we call it. It should be the case that the second derivative in time of this variable equals some constant times the variable itself. So far, cosines and sines are the kind of functions that do that. What I'm trying to say right now, when I say that something works or that something's a solution, I'm always trying to contrast it with something like that wouldn't work. Like I would never say something like this. I would never guess tangent, because if I take the derivative of tangent, like first of all, I don't even want to, but I think the derivative of tangent is like secant squared or something. And then if I take the derivative of that, it's going to be some bigger mess like cosine squared minus 1 all over blah, 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 blah. No way in heck, if I take derivative of tangent twice, am I going to get back to tangent? And that's the requirement here. We need functions that when you differentiate them twice, you get back to the original. Even something like 1/2 AT squared doesn't do that, because when I differentiate it twice, the t's go away completely. I just get some letter like a. So cosines and sines seem good so far, but what this problem is getting at, this next homework assignment question is saying is, well, wait, you know what? There are other functions in the world that do that. There are functions like e, where with e to the x, the derivative of e to the x, like whatever x is, the derivative of e to the x is simply e to the x. It's kind of a crazy function that way. In fact, it's like the coolest function of all that way. The derivative of e to the z is e to the z. The derivative of e to the omega t, well, you still obey the same rule. The derivative of an exponential is still an exponential, but you have to throw in the chain rule or something so to watch the details. But I'm saying, unlike algebraic functions, unlike something to raising the variable to some power and then multiply it by a constant, we're not multiplying t by any power here. We are raising some number. Sorry, let me back up again. Unlike algebraic functions, or unlike the tangent function or something, the e function also seems to spit back something similar after you differentiate it a couple of times. Cosine, you literally had to differentiate it twice to get back to cosine. Like first sine, negative, and then you got negative cosine. You had to go through it twice, and when you got back to cosine, actually, there was a negative sign all of a sudden in your life that might otherwise be annoying, but somehow Hooke's law said needs to be there anyway for the physics, so that was good. With e, also, we're going to get back to e if we differentiate it twice. We don't even have to differentiate it twice as far as e is concerned, but so there's a reason to test e functions. Like they seem like they would have an important mathematical property here that's relevant, so we try it. Is it a solution? Why not? Oh, I went backwards. So I go and I try it. I take the first derivative of, where'd it go? I take, here we go. Yeah, if x equals e to the negative omega t, then the derivative of that is, from chain rule, negative omega e to the negative omega t. Maybe someone should stop me here. Oh, let me see the chat. But we're still doing the same thing, just testing a new function. And we're allowed to test anything, but I'm trying to explain the motivation why we tested. Then I differentiate it again. So I do chain rule again. So the negative omega comes out again. So now omega gets squared and the negative sign gets squared, so to speak. So now the second derivative, and here's where people in the homework made a mistake for whatever it's worth. So it would be very legitimate in a minute to ask a question, like some people are clearly confused and other people may not have realized that they were. But I'm saying here, we took a function that looked good. It had the right kind of shape. It had the right basic idea, which is that differentiating it gets back to itself. But here, the negative signs don't work out as cleanly, at least in this one, where we stuck a negative in. If I differentiate it twice, I get, well, I'm going all the way to, like, if I differentiate it twice, I got omega squared times e to the negative omega t. So I can make that substitution. That's what you are supposed to do. The same thought process as I did on stuff that works. I substitute in x for e to the negative omega t. But even when I do that, the problem is I get back that the second derivative equals some positive constant times the x, not a negative times that. Like, let me back up one word. K is always constant. The stiffness of a spring is never negative. The mass of a spring is never negative. Omega, number of times you go back and forth in some number of times, is never negative. You can't have a frequency of -3. It just doesn't make any sense. So whatever is, so we're off by a negative sign here. I'm going to pause for a second because this is what a lot of people got this wrong. So, and I know everything I've set up until now is probably boring and lost people. So let's just pause and catch ourselves up. We're in part G and H of Roman numeral 1. I'm saying that the exponential function that I just decided to test didn't work. Doesn't mean you did anything. That doesn't mean you did anything wrong. It just means you should get like false as the answer here or something. In order for this to really help us and to make sure we're on the same page, what I'm going to do is I'm going to assume people hear me, but I'm going to pause for a second and say, look, if I'm getting this, if I'm you or listening, I'm like, okay, yeah, I get your point. All right, you have to be careful. The E sounded good, but then it didn't work because negatives we're really being picky here about negatives. And we are. If there's no negative sign, then there's no Hooke's law. There's no restoring force. There's no back and forth. There's just fly off forever. And okay, and that's what happened here. But you might say, well, that's your fault, Yaverbaum. And you put the freaking negative sign in the first place, like what, to trick us or to waste our time. Like there, you wrote, Yaverbaum, and this is true, Yaverbaum, you wrote, assume x equals e to the negative omega t. And then negatives cause problems in our life. So no wonder, like you, like jerk face Yaverbaum, like if you don't want negatives to cause a problem, how about trying one without that? So I want to say to everybody, very good question, glad you asked, and asked so politely too. Could everybody right now, since it wasn't in the homework, can you right now just try the exact, to make sure you get this as fast as or slow as you want. Let I'll write it down, but let x equal e to the positive omega t, and test real fast whether that solves the problem or not. Like test whether x equals e to the positive omega t is a solution or not. It would be good practice for everybody. Please take 2 seconds to do that. I'm going to write the question again so you know what I'm saying, but this would be a good time to catch up and figure out what we're talking about. I'm saying now. This wasn't in the homework. It's a sidebar to make sure we're getting it. Assume there's no negative sign in what I tested. So you can say, the question I'm always asking is either, is this a solution to, or you could say, does this solve, or you could say, does this satisfy, all the same thing. Does this satisfy d to x? Okay, we're trying to find out, does that example of a function, like an expression that just has x and t, those are the only variables in it, and a bunch of other constants, does that relationship ultimately contain information that's consistent with our differential equation? That's what everybody should be testing right now for a second. It basically means take 2 derivatives and see. And yes, I see, cool, I'm seeing, cool, this is great. And feel free to do this, yes. So I'm seeing private chats because we're humans. I'm seeing private chats, which first of all, every private chat I'm getting on this. Oh, I'm sorry. Oh, I see. Blah, 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 blah. Right. Yeah, good. Now we're talking. All right, look, now people, I mean, everybody who's saying something privately or not is saying something exactly on point. Everybody is on point. I mean, who's saying anything? Okay. And even if you think you're a couple of steps back, and even if I end up saying no to one of your questions, it still means it's the right question. I'm going to answer this. For one thing, also, I'm sure you've already noticed about my speaking style. It's very helical, my speaking style. Like I'll go around and around, and the hope is I'm always going forward sort of while I'm going around and around, but I do, which just means to everybody, if you start feeling like you're losing the thread, like you had the thread and then you're starting to lose it, which always happens in physics. Like, even if it's partly because you zoned out or whatever, if you're starting to lose the thread, it is good that people hang on. Like it is good. The thread can come back to you if you just hang on, even just by paying attention. Because we're not monotonic here. But that said, on these questions, yes. First of all, I'm assuming one thing, a calculus thing. I'll remind you right now. Let me make a new page. I am assuming the following. Okay. I'm just saying some math that I'm believing that I'm just believing this math is true. It may not be fresh in your mind. You may need a refresher, but I am believing like given, if y equals cosine of x, for example, sorry, if y equals sine of x, I'm assuming that we've proven somewhere in our head, somewhere in our life, that the derivative of that is cosine of x. Like I can, again, try to work that through with anybody, but yeah, I do believe it's true. I similarly believe that if y equals cosine of x, then the derivative of that is negative sine x. Okay, I was assuming that 2 days ago, but now I'm also assuming here, this is the part that people may not remember. I'm now looking at a different type of function. I'm adding exponentials now. So yes, I don't know why everything has to be, I'm such a New Yorker. I'm assuming if y equals e to the x, then the derivative of that is literally and simply itself. It's the only function in the world that is like that. Like even 2 to the x is not like, literally only e to the x is like that, but it's the point of e to the x, really. It's the one and only one function whose derivative is itself. So which also means that its second derivative is also itself, etc. Okay. But I'm assuming chain rule is true too, right? Just quick refresher to everybody. And I was assuming and using chain rule with the cosines, but I am assuming, hello. Sorry, I'm assuming this quick, and then I'll get back to the squaring and the negatives and all that. All right, I'm going to stop with this black background because it wastes too much time. I'm also assuming chain rule. That's why I do the black background. I know, Grimace Frog here first. Sorry. All right, I just want attention. I'm assuming this chain rule. If like z equals some function of y, and y is some function of x, right? I'm just reminding you chain rule the fastest way I can. Chain rules, like if you have a function within a function, right? We assume that to take the derivative of a function within, we don't assume, we've proven in other parts of our lives that if you take the derivative of a function, in order to do that, you take the derivative of the outside everything, and then you multiply by the derivative of the inside, which is just to say this. We're saying we believe that dy dx is the same thing as dy dz times dz. If you think about it, this is what the chain rule actually makes total sense if you write it this way. If you join me in thinking of derivatives actually as ratios of differentials, things start to actually fall in place. The chain rule just says if you want, the derivative of the derivative of, if you want the derivative of a function, well, it's the derivative of the outer function times the derivative of the inner function, because why wouldn't it be? Obviously that's not really a proof, but the application here is that I'm saying that so if we have a function like y equals a e to the x, then dy x equals. Now I'm about to write it. Now here's, by the way, I think this is helpful to people, hopefully, like those math moments. I encourage all of you, even if you think you're totally on, even if you are, totally on top of math and none of this bothers you and you love it and you're completely in command of it, I still encourage you, please, to write these things down as I write them down, even if it's not to teach yourself something new. Partly, this is a handy way of seeing the kind of notation that I use to do these. Partly, it will, I hope, show you things about the notation and the use that you might not have noticed before and how it applies to physics, blah, blah, blah. You'll notice one habit I have. Whenever I'm doing the physics, I try to talk in terms of like x and t or something physical, position and time. Whenever I'm talking about the straight math, I try to just go back and make it look the way it would in the math class, arbitrary y, arbitrary x. I want everybody to join with me in being that facile. I want people to not, to know that letters are all just numbers, and different letters for the same thing are just that, different letters for the same thing, but different types of letters function in different ways, right? So y and x I'm using as variables. It matters deeply which one is the dependent, which one's the independent. But then if you see me just throw in something like a capital A from the beginning of the alphabet, you should assume that means some kind of constant, right? Don't be bothered whether I say A or X naught or whatever. So in this case, given the exponential rule I just quoted and the chain rule that I'm just quoting, not proving, then the derivative of something like this would be like, the derivative of the whole, sorry, that's so stupid. Sorry, say we have a function like this. Okay, derivative of the whole thing, well, the derivative of the whole thing, sorry. I shouldn't be dragging this in, I suppose, but. Nope. Yeah. Okay, so it's going to be equal to, in other words, a bx times the derivative of the thing inside, which is to say b. So just as a quick review, if I have something of the form a times e to the bx, then the derivative of it is a times b times e to the bx. That's fast, but does that? Okay, now, did I ever answer? Right. So hopefully that's sort of just a refresher on what I'm doing here mathematically. But now to get back to the question, I'm saying that if I tried, Yikers Island. Oh, yes. If I tried, it was in the sheet. No, it wasn't. Sorry. If I tried this thing that I just asked you all, which is what about trying x equals e to the positive omega t, right? This could just as easily say y equals e to the positive lowercase bx. Like it's the same math, but if I do that and I want the derivatives, well, dx dt is going to be omega e omega t, just like what I just did a page ago, only here capital A happens to equal 1, so to speak. But this is the first derivative. And then the second derivative, I do the same thing again, exponential with chain rule. And so I get omega squared e omega t. I'm going to pause for breath in a second. And what I'm claiming is that's very nice. Like that is cool that if you take a function like e the omega t, which means something, I mean, then the units mean something. But if I differentiate it twice, I get omega squared e omega t. In other words, I do get back omega squared times x itself. Like, yeah, that's what x was. So that's nice. There's something cool going on there. But omega is definitely positive. And my original differential equation that we're trying to solve, the thing that we are really concerned about here, the thing that we're always comparing everything to or trying to solve, looked like this, right? Omega squared, fine, x squared, but there was a negative before that omega, and that's not an arbitrary difference. I mean, omega can be any positive constant. So if you put a negative before it, the whole right side is negative. But here, what happened when I tried this solution, I didn't get negative. So what this means is this thing that I'm trying, this e to the omega t, is physically significant. It is the solution to some kind of differential equation. Perhaps it is the solution to what's written at the bottom of it is the solution to this, but that's interesting to a mathematician. The whole reason we're looking at differential equation in the first place is because the physics popped it out. The Hooke's law says that springs behave this way, as in orange, as in they always have a restoring force bringing them back to some sort of equilibrium. We're now saying, thanks to math, we can relate anything in life at all. We can relate lots of things in life to masses on springs. But in order for that to happen, there's got to be that negative sign here. So e to the omega t is not a solution. The one in the homework, e to the negative t, was not a solution. Like it looked close, it looked almost good, but it wasn't. And this still isn't. Are people with me? Am I making sense, sort of? Again, we're going to keep, wait, go back to the other screen. Definitely, yes. Hold on, go back to the other screen. Tell me which, I don't know which screen. Wait, ooh, sorry. I know you don't want that. Is it, I don't know which screen. Oh, okay, cool. So what's going on here? There might be a frustration. Like what's going on here is I'm playing in the we are playing in the sandbox. Like we're literally poking around and experimenting with some mathematical idea. We're like thinking, oh, I think I get what it means to satisfy this certain constraint. So I think I get it, and I think I even get what's required to satisfy that constraint. So I'm trying other things to see if they would work too. Like it's as though I'm, Hooke in the first place, like trying to fit a mathematical model and develop it for the physics I have in front of me. I have strong reason to believe that exponential functions should somehow help me describe springs, but they seem to keep throwing me off whenever there's in that negative sign way. So I try one more thing. In the homework. We get to the next question. It was, yeah, all of a sudden K, I now throw in, because I keep going back and forth with -1 and +1, and that's my nightmare, I just get clever and try something that's funky with in its reference to -1s and 1s, and that is I. Now, I am definitely not assuming anybody in the class took any, I mean, it's thrilling if you did, but there's no requirement that anybody here took like functions of a complex variable or blah, 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 all great courses. But the one and only thing that I'm assuming that we know about I, or ever have heard or need to know here, is its definition. Like every reference I ever make to I from now on in physics is just going to come back to relying on one essential property of I, and that is that it's defined to be the square root of -1, right? Because we need it to expand our number system to account for that concept, because no number on the real number line when multiplied by itself will yield a negative. Of course, it's stupid to call it imaginary. It's no more imaginary than any other number, but it is a sophisticated kind of number. But that's all you need to know about it is its definition. This is my plea for physics 2. It's that it's defined to be square root of -1, square root of -1, whether or not you think that could be useful or not. That's what it is, and so we're going to use that as we test out things. We're suddenly trying x equals e to the I omega t. That is a mouthful. That looks like some math that nobody wants to deal with, maybe. But all we're asked is to check it, i.e. differentiate it twice. Here's the work. Sorry, wait. Actually, I don't even remember if I got the right answer. I think I might. Well, let's just do the work. We have to see if it's a solution. So we're going to take derivatives. Oh, didn't mean to do that. Okay, so here we go. We're testing out. Maybe you want to take a moment and look away from me but we're testing x equals e. Oops. Yes. To the I omega t, right? And the question is, does it satisfy? And we're doing this over and over because it is that new. I know it's getting repetitive and things won't always be like that, but if it starts feeling repetitive to you, that means you get it, so that's good. So does it satisfy this? That's always our question. I think I'm yelling too loud. Excuse me. So I take derivative number 1. Okay, derivative number 1 using, and by the way, yeah, derivatives of I, like what's up, Yaverbaum? Now, I is just a number. It's the number that we just wrote up there, square root of -1. Like, do you have, is it a funny number? Sure, but it's just a number, i.e. it doesn't change, it's a constant. So whatever, I'm just going to treat it that way in all these derivatives and no loss of dignity. So the first derivative would be I times omega, because of chain rule, times e to the I omega t. So I'm just doing chain rule. I'm just treating I like it's some number because it is. And then I take another derivative. Hello. So then I take the next derivative. And so I bring out the I and the omega again. So I have I squared omega squared like this. Okay, so what? Well, can we simplify this? Well, we can, because I squared by definition is -1. I mean, I is a square root of -1. So this is -1 times omega squared times e to the I omega t, right? And so this is negative omega squared e to the I omega t. So I want to argue, and I may have said this wrong. So if this was the original guess here, then it would seem that this one does work. And I'm not even sure if the question, this one I say yes. And I think I said no a second ago on one page. But the answer is yes. I'll erase it on the other page. I is a constant, absolutely. Yes, I is a constant, 100%. And if I is a constant, assuming that, or believing that I is a constant, then what we really just showed here is, and it's a little bit, again, well, what we just showed here is, okay, to satisfy this differential equation, we need some kind of function where taking derivatives doesn't make the function simpler, where taking derivatives gets you back some form of the function. Exponential, so we decided to try exponentials. Exponentials by themselves didn't quite work because there was a negative problem. Either way, whether you threw a negative sign in or you didn't, it didn't get double bounced the way, or it got double bounced, like because a negative. I guess that's what someone was saying in the chat, because each derivative returns the same thing with exponentials. We don't sometimes get rid of the negative and sometimes not, the way we did with cosine and sine. So the negatives got us into trouble, but then we just decided to throw in an I, which was a bold move, and throwing in the I made it seem like this worked, which makes it seem now, here, quick side, and that's true, it did work. Quick sidebar, just so you, because there's beautiful mathematics here, but quick sidebar, we seem to be suggesting so far that if we have something that, if we have an oscillator in general, like if we have some measurable quantity that seems to be doing something like this, right? Whether it's the position of a mass on a spring or the angular position of a pendulum bob or something about the electrical current through a RC circuit or something. If Z is a measurable, which can be described by this differential equation, then what we're saying so far is Z oscillates in time and can be described by some combination of sines and cosines. Let's say that. Right, some combination of sines and cosines and appropriately placed constants, some of which might be zero, right? We're saying that, but now we're saying that's a solution. But now we seem to be saying, it would also work to do something like this, or even presumably, since it didn't matter that we didn't put in a negative sign here, presumably if we had put a negative sign, it would get canceled out twice. In other words, presumably this would work also. We'll just say this. Now that's weird, and it's true, by the way. What we just showed is that whatever you can accomplish with cosines and sines in combination, you can apparently also accomplish with exponentials as long as you throw an imaginary number in. And that's a very weird thing. Again, quick sidebar here, sort of a sidebar, but it's a little bit weird if you're trying to get a physical feel for anything I'm saying, which you should be. If you're trying to intuitively, conceptually picture any of this, all we have so far is a mass going back and forth on a spring. And I'm trying to say that whatever you can ever picture about a mass going back and forth on a spring will apply and serve you well with anything in the world of identical mathematics. Only what's strange is that cosines and sines, I think you all believe me, like they seem like back and forth, like on face appropriate functions. Like cosines and sines, their graphs look like the kind of thing I think we're talking about here, back and forth cyclically. Exponentials tend to look like this or like this. I mean, exponential growth or exponential decay is something that generally goes monotonically, gets better and better or worse and worse with increasing drama. So how could you possibly describe a mass on a spring with an exponential function? Like that seems to make no sense if it's supposed to cycle back and forth. And indeed it doesn't. If you just do a normal exponential function, it doesn't work. As we saw, the negative signs, just that business of the negative sign all of a sudden means an exponential can't be used to describe something under the influence of a restoring force. However, throw imaginary numbers into an exponential function, in other words, do a complex function of an exponential, and then somehow that captures oscillation. Like, why on earth? In other words, we seem to be suggesting that there's some relationship between sines and cosines, cyclical stuff, and complex exponentials. There's no obvious reason why there should be, and because it's not obvious, it's why it's worth saying. But there is a reason to see why it's reasonable once you think about it. That is, and here back to the homework, and then we're going to move on to the next. But just note this. Note the reason. I am literally saying it's something called Euler's equivalence, and I've seen your homeworks. I know some of you have seen this in other classes, which is terrific. But most of us get deprived in our lives. Like there is a literal. Well, it's literally true. Let me see. Yeah, there's a relationship between trigonometric, exponential, and complex functions. It is this. Yeah, note here, and you may actually want. I want people to write this down actually, so it's going to go slowly for you. Note, just write down y equals. Well, write down what it's writing, but you're just going to take sine of x and differentiate it 4 times and watch what happens. Then you're going to take e of x, differentiate it 4 times, see what happens. A lot of you already know, but just write it down so you can make a comparison. So I'm saying, like, say we start with the function cosine, right? We call that the function, like that's the original function. So we'll call it derivative number 0, so to speak. Like the original function is derivative number 0. You take 1 derivative, you get negative sign. Take 2 derivatives, as you're seeing here on the board. 2 derivatives, you get negative cosine. Oops, sorry. Okay. 3 derivatives, you get sine. 4 derivatives, you're back to cosine, right? It took 4 derivatives, and cosine goes all the way back to itself. Just like note, right? Then on the next page, or stop me from going too fast, but then that's what cosine does. That's why we've been using it from the start. Note on the bottom of the page, if you choose an exponential, if your original function is e to the x, i.e. your 0th derivative is e to the x, well, then you take a derivative, you get e to the x. Take another one, you get e to the x again. Just like do it 4 times, you get back to the original, just like cosine. Indeed, you don't have to, with e makes it easier on you to do that. But what's common so far between cosine of x and e to the x is both of them meet themselves back up after 4 iterations, right? Well, why am I bringing that up? Because if you look at I to the 0th power, right? Anything to the 0, any constant number to the 0th power is 1. So I wrote that down. Oh, I guess I should. It's just going slower now. It's the same thing. I to the 0 is 1. I to the 1 is I itself, I, right? And maybe, again, you want to just try this on your own without looking, see if you follow me. I, by definition, is -1. Well, I squared is -1 times -1. That is, is a square root of -1 times the square root of -1. That is -1. I to the 3rd, how can you get that? Well, it's I times I squared. Look what's happening. And you might guess where I'm going with this. I'm trying to show, and it's filling in a funny order, but it'll be all there in a minute. I'm trying to show that one indicates there is a relationship between exponentials, complex numbers, and trigonometric functions, 3 things that seem to have nothing to do with each other, really. The relationship is that they all cycle in 4s. And that is the relationship. And of course, there's deeper ways to say that. But what it ultimately means is that, just as a side note, just so you know, something that can be proved if you ever, I just can't, if we come this far in physics, I can't resist just at least saying once, this is true for all times.
Professor, when you have a moment, can you go back to the last slide? I just didn't get to finish copying it.
Totally, yes, sorry, yes, absolutely. And just for the moment, just writing this, I'll go right back to the last slide, or equivalently. Wait, I'm missing something here, right? I think that's right. I'm not totally confident about my rearrangement, but this thing on top is called Euler's equivalence. You can prove it with Taylor series. If you've ever done Taylor series, it's easy to prove. And we might talk about Taylor series another time, but you don't have to know this thing that I just wrote. This is the first thing I'm saying. You don't have to know, but it's very cool to just stop and pause. What it's just getting at in the end is that there's 2 types of functions in this world. There's 2 types of functions in this world. Wait, no, do I want to say that right now? What I'm trying to say right now is a differential equation where we left off. Oh, sorry, let me go back to the other slide. Sorry. Was this the slide that I was asked to go back to? Is this what people?
Yes, thank you. I got it.
Okay. All right, cool. Okay. Now I'm going to leave. Okay. I've said it. Well, the thing I'll say in English now, I'll say it again at some point. Remember, nope, changed my mind again. Last mind change. Because this is where we left off last week, and because I know I'm starting, this is where I start to lose people generally, and people start feeling fuzzy. Fair enough. And some of the stuff you have to, let sink in and think on your own. Just realize I am going to say it over and over again. So if it's starting to feel fuzzy, that just means you're starting to get your tuition worth, and that doesn't mean that you should start zoning out and start losing confidence. It just means like tighten your grip, whoever anybody is, because I'm just trying to put this all in a big perspective. I'm saying last class, it's true that in principle, what we've been doing for the last couple of classes is finding solutions to the differential equation that describes the physics of harmonic oscillation. Like that's what's supposedly going on here. But of course, the backstory is that I'm really trying to really give context on what it means to be a differential equation and what it means to solve it and why. So the reminder from last class is, look, remember this, okay? This, or let me be more general. I'm sorry, this is a math point I'm trying to make. So let me be very general if I say something like this. Okay, this, for example, dy dx equals ax. Technically speaking, that's a differential equation. Sure, like technically that is, because there's like a derivative on the, but for all intents and purposes, that thing that I just wrote, not only is it a kind of a simple version of, you know, an equation that has derivative in it, but that thing is not a differential equation. Like nobody would take a whole class of mathematics or devote any time worrying about there's nothing, this thing right here is not what people mean by a differential equation. This thing is what Antonio and others showed us last time. This thing can be solved by saying, oh, by multiplying both sides by dx and saying, oh, this, and then differentiating both sides and then saying, oh, y must equal ax squared over 2 plus some constant. I just did that fast, but look carefully. What I'm saying is we're looking for a variable related to another variable. But someone's on physics has unfortunately given us derivative information rather than direct information. What I'm trying to tell everybody is just because we were given a derivative instead, that's not really the meat of the issue. You can be given a derivative instead of what you want, and you can, and if it's given like in this way, you can just work backwards, anti-differentiate or integrate and get what you want. What the issue that we're dealing with in this class that's so much deeper and more interesting is we're dealing with a guy who cannot manage technology named me. No, we're dealing with, well, yes, but, and I did it again because I'm so excited about this differential equation. We are dealing with personality disorder plus spectrum plus overintelligence. We're dealing with something that looks like this, and please scroll back and forth between the 2 pages. Like I'm saying, this is a differential equation. This is simpler than the one we're dealing with class. It's like a very simple one. It's maybe the simplest possible one to solve, but it's still way less simple than the thing I did on the other page. This is a differential equation. This, you cannot just integrate both sides. You got to do something smart mathematically, but more physically, what I'm saying, this is, and this is life, this kind of equation. This is interesting because this says that the rate of change, this says rate of blah, 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 rate of blah, 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 depends not on cause, but on effect, right? If you think of a dependent variable as an effect, and you think of the independent variable as a cause, I mean, that very loosely, like if you figuratively think of it that way, this here, any differential equation says that the derivative, the rate of change, is some function of or is related to the dependent variable, the effect. It's it necessarily, in other words, if you're and this require, I mean, to be straight up, how would I ever solve this? If I want to solve this, which is easier than what we're doing in class, I'll just do it fast just so you see. To solve this, I know I have to make up my mind about black and white. I'm like America right now. So, to solve this, a y, the fact that it's, and by the way, there's nothing different between y and x as letters of the alphabet. There's no rule that x can never be a dependent variable. What is a rule though is if you write a derivative this way, whatever's in the numerator is the dependent, whatever's in the denominator is independent, like it's rise and run, right? That is a rule, and that is what I'm watching here. So if anybody ever tells me that the rate of change depends on the dependent thing, not the independent thing, mathematically, what I have to do is I have to say, oh, well, then I guess I got to flip everything. I got to say something like dx dy equals 1 over ay or something, right? And then multiply both sides and say something like, okay, fine, then I guess dy equals equals dx over ay, I think. Is that what I'm saying? Yeah, like this is a totally different problem now. If it's a deep, so now I say dy equals dx over ay, that's an a, right? And no, if I already screw something up, d 1 over dy over a, oh yeah, dx, oh no, I did it wrong, that's why. Now I have to say dx equals, God, someone might help me. I can't literally remember what I just wrote a second ago. I want to say it's this. Is this what I'm saying? Dy over a y. Oh, I'm losing my mind, sorry. Okay. Right, someone correct me. I believe this is what I'm trying to say from over. And that means if I want to differentiate both sides now, right, I'm going to get something complete. I don't know if you're following me or not, but I'm saying if this is the case, this is a totally different kind of answer. People with me or no? This is important. This is not part of the whole, I mean, this is due to the homework. This is why I assigned the homework, but this is now a sidebar. And it's, again, from Wednesday. I'm saying, like, we're pounding our heads against the wall in order to fit solutions to differential equations. Differential equations are completely within our grasp and necessary as physicists, but they are something different from just an equation that involves a derivative. I am trying to say that necessarily any differential equation relates a rate of change to a dependent variable. So in English, any differential equation necessarily involves feedback, like the mathematical and physical word for what is happening in any differential equation is that cause is leading to effect, which then becomes its own cause, which leads to effect. The classic example, again, is like compounding interest in a bank. If you get an interest-bearing account, that means the amount of money that they add to your account every day is based on how, or every whatever unit of time is based on what's in your account. But what's in your account, of course, is based on whatever was put in your account that minute. So there's this feedback that is captured anytime you say rate of change is equal to a function of dependent variable. And why am I saying all of that? First of all, that's why we're caring about situations that almost seem like they shouldn't be solvable. It's almost amazing that they are. But whenever they're solved, look what happens. You always get funky functions that involve logarithms or exponentials or sines or cosine. The solution to any, so in sum, what does all this amount to? I'm saying this. All differential equations all proper differential equations, like dy dx equals some function of y, not dy dx equals some function of x. All differential equations describe feedback phenomena. The most widely known familiar version of feedback is like literal auditory feedback, that screech that you get when you put a microphone near a speaker. And think about it, that's exactly the kind of thing we're talking about here. Putting a microphone into a speaker means it comes out of the speaker, goes into the microphone, which comes out of the speaker, which goes into the microphone, and it feeds off itself. And it builds and builds and builds until it's a very awful experience to the ear. But you can imagine if pitch represented money and that was money doing that, you'd be psyched. All differential equations describe feedback phenomena, and the solutions are all, these kind of functions are all what are technically called transcendental functions. Functions that are infinitely differentiable. Functions that when you differentiate them, you don't get simpler and simpler things that eventually reduce to zero, but you get functions themselves, transcend. And then we're going to stop. I know this is a mouthful for a lot of people. Transcendental functions, as opposed to algebraic functions. Okay, that's a mouthful. So that was a lot. What did it have to do with anything? We have to bring it back to physics. Okay, I know we have to, I know there's also the vectors in the sheet, but and I know there's got to be questions. Oh, hands, okay. But one thing, I want to get questions, but am I right that have we at least finished going over all the parts of the sheet that were not the vector, like just in terms of getting answers? I think that, could someone confirm or deny that we just finished? Well, I'm going to assume we did. I think we have no more to do in the sheet except for all the vector stuff. Is that true? I mean, in this homework. Well, okay, I'm going to assume it's true. But or people just had questions. I think. Numerator's dependent, right? Okay. Wait. Just addressing chats. 1 second. We're going to well, hold on 1 second. Sorry. Okay. Oh, yes. Thank you. Yes. There's a. Oh, go back to the other. Okay. First, I'm going to go back to the other page. Sorry. But yes, you're right. There is more, although I may go much faster through it. I think it's, but yes, the page about feedback phenomena, I'm going to go back to, and then I'm going to. Oh, it's 3 o'clock in this instance. You know what? I'm going to put whatever page someone's at. Oh, cool. 1 second. Does anybody, what page? We're going to take a break in a second. I just want to make sure we're on the same. Someone asked me to go back to the feedback page. Oh, this page? Someone's at, whoever needs me to go back to the page, was it this? And all this will be recorded too. I mean, it is recorded, but here's what I think we should all take. Let's all take a 5-minute break, like go get a soda, whatever. But if you think of what your questions are on this while you take a break, but let's all take a break for 5 minutes and we'll come back and answer questions. Yeah, including me. I'm going to turn off my stuff. Right. Okay. Okay. So I'm back. I don't know if people could. What's scrolling now? So I'm back. Well, what's scrolling? I'd like to take questions most of all, but what's scrolling now? I think this might be with the next part. Before we get to the vectors, if we won't do the vectors today, that's fine. But the next part is kind of plug and chuggy. So I'm thinking about just letting this scroll so you can see what I did and see my answers while you ask questions. It might save a little time, but definitely stop me on any of these screens. But I'd like to take any questions that there are right now, please. And if they're not, I'm just going to do like this is the rest of it. I feel like this might be better than me over talking it. But so please ask any question about what we're doing so far or anything you see happening here, and or write it down if you got any of it wrong. But this is the rest. In the meantime. So I'm just going to keep, I know this is weird, but I'm just going to keep, stop me if you see anything that you need and I'm going too fast, stop me if you think it's all, but this is the next. All that's really happening in this part of the homework is we're just, we're getting familiar with the function and plugging in back and forth to make sure we know how to use it. But really what we're really trying to see here in this part, we're really trying to see is what impact the phase constant, that phi term, has. Oh, okay. So these different back and forth plug and chug questions are really sort of trying to show you that how the thing moves back and forth would be the same for both those functions. It's just that one gets a head start by like a quarter of a cycle versus the other. It's just sort of making sure that you can see how to tie the back and forth nature of cosine functions to the back and forth nature of this spring. But again, I'm not saying any of this is easy. I'm just saying it's sort of boring to listen to me talk about all the. So stop me if any of this does or does not make sense. Sometimes it's asking for two values and sometimes it's only asking for one, but that's going on here. So I'm not going to scroll this way through the vector stuff. I'm going to hold on, but I am going to just keep doing this right now. This is what and of course, this whole recording will be posted so you can also check later, but this is what I did for this part of the homework. What else am I assuming? Yeah, stop me. I'm just going to, this is, at this point in the homework, I'd only started asking for one value, but this is part 5. I don't know if this is doing anything for anybody, but again, if you're just checking your answers or whatnot, this is lowercase Roman numeral 5 from part A of the, oh wait, what was the, oh good, I'm glad someone's, okay. What was the answer for 5? Oh, sure, I'll go back to 4. I don't even know. It's 4. Oh yeah, so I think that's a good question. So I think, and we could pause there. So I think the answer to 4, if the question was at what times will x equal -4, I believe the two times are 1 and 3 seconds. I mean, presuming this whole thing, these are kind of math questions, so it didn't actually specify whether it's in seconds or minutes or what, but assuming everything's in seconds, I think the answer to 4 is, oh, okay, cool, okay. But again, if anybody didn't get that answer, I'll tell them. So that's 4. And then, and again, we won't do this every time with all homework. I just want to make sure we're getting off on a strong start over there. So there's that. Again, if you haven't gotten homework 2 back yet, that's no reflection on you. It just means I'm not done. But homework 3 was due, so I should get to that next. This is 5. So, and all this assumes that we all know that that the maximum value of cosine is 1, the minimum value is -1. So this is that. Again, anybody stop me? Okay, and now it goes to B, where it's going to ask the same skeleton of questions, but with this function. The real thing is ask yourself, do you understand that by putting the plus, like we're just contrasting this with the last one. And what's significant is this right here is the phase constant. It means that we've got an oscillator that started in effect a quarter cycle behind another oscillator. Quarter cycle, because a cycle is 2 pi, so a half cycle is pi, so a quarter cycle is pi over 2. That means, you know, when one of the, picture two masses on two springs, when one of them was at equilibrium, the other was at its maximum stretched point, or the reverse, something like that. And by putting a 2 pi before the t, I hope everybody understands, this is a red herring right here. They use that expression on YouTube a lot, I think, but this 2 pi is just to be obnoxious, right? If you get what's going on, by me putting that 2 pi, it means, you know, when we plug in, I might get different answers for different things. But just by putting that 2 pi, I haven't changed anything, because that just, I take that back. That's too glib. But the thing that we're studying right now is the pi over 2. So we're just studying, we're just like comparing what happens here. And I think, in other words, it's saying when the other one started, when the other one was at position 4, this one was at equilibrium, etc. So I got this. Sorry, that's annoying. And then we're almost done after this. I'm just slowing this down because I know if you're writing at all, it's not fair for you to have no time to write. So this is just to gauge on it. And you should be writing. But I'm assuming I think we're more in bored but clear land rather than excited but confused land. It seems like. I think there's just one more disclosure, and then let's see, then. Right, that's that answer, and then we're just about. I'm just going to leave this up. This is the next one. The vectors I'm probably going to do tomorrow. We do need them very soon, but you don't need any of the vector stuff for homework 3 or 4. Homework 4 will be posted right after this class or shortly thereafter. It won't be super long because I know you have class tomorrow and lab and all of that. But the real issue is, I know before this class, about 2/3 of you handed in homework 3. I definitely, if your first priority is to do homework 3, whatever I post or whatever, and it might have looked intimidating to people at first, but I think after all of today and after last time, homework 3 is sort of our last version of just practicing this, and then we move on. So please do it, but in other words, we're going to shelf the vectors is we don't need yet. So are there any, I think this is the very last question. Yeah, are there any questions on any of this cosine stuff? I would even, quite frankly, at this moment, I'm not going to go to the vectors. So with the little time we have, I would take any questions from homework 3. In fact, yeah, I'm going to go to homework 3 before I even deal with these vectors thing. And again, if you didn't hand in the vectors yet, please still do. And don't worry if I go out of the order. It doesn't affect your grades of turning in. But I think homework 3 makes a lot more sense right on the heels of everything we've just said. So I will certainly take questions from homework 3. And for the last one, can I? Okay, last one. Yeah, for the last, there's certain, yes, there's more than one value that t can equal for most of these questions. And at some point in the homework, it started just asking for only one value of t. Like, so for the last one, right. For t, t can also, oh wait, maybe I made a mistake. I am only solving for one value of t because I think it only asked, but maybe I made a mistake even. You're saying, or I'll pick up on this. You're saying 1/2, not 1/4, I think. So let's check it. All right. This is worth everybody checking here. On question, I'll rewrite it in a second, but lowercase, for the third part in B. Oh, for the third part in B. Oh. Wait, the third part in B. The third part in B. Oh, I think, sorry, one thing, I just presented these three orders in the raw. If you look carefully, I just presented 3, 2, 1 in a instead of 1, 2, 3. This right here is the answer to question. I'll answer that question in a second. Here's the, let me do this in order, sorry. B1 is right here, I believe. So B1, when t equals 0, what's x? I get x equals 0, which, by the way, that's exactly the point, right? Like normally oscillator, if we just look at one oscillator, we pull it back to some position and let it go from there at t equals 0. If we pulled it back to 0, if we just have one oscillator, they don't normally start at x equals 0. This oscillator is starting at x equals 0 because it's specifically a quarter cycle out of phase with some other oscillator that started where you'd expect. But anyway, so the answer to question 1 here is x equals 0. Then question 2, the answer is the very first answer is t equals 1/4. And then answer 3 here is t equals 0 for whatever that's worth. I hope to post, generally I try to post the recording because someone just asked, I will try to post this recording tonight. Sometimes I have problems. I mean, there's so much upload and download time and limited Wi-Fi for all of us in quarantine, blah, blah, blah. So I try to get it up tonight, but if I run into problems, you might not have it till tomorrow. But I especially since I'm not editing them and that you have to go through all the crap yourself, I should be posting it in a few hours from now, assuming it worked. But that said, if no one has questions on the cosine, well, if there's no question, I'm making a quick decision in my mind whether I want to. All right, no, what the heck? We might as well all right, well, let's knock off this sheet. Since it is 3:20, we have time. I mean, I think this is, sometimes things are a lot because they're so intense. I don't know that this is just a lot of sort of dry stuff, and I apologize, but we're just getting all the math out of the way that we need. So we'll continue with the sheet now and do this vector business. Again, I posted 2 lectures about this, about the details that some of the deeper details that we need for later, but the straight up stuff of the vector last bit of this sheet, the fundamental point is just this, and then I'll start writing the answer. Actually, well, yeah, the fundamental point is this. Okay, there are 3 fundamental ways that vectors could be involved in some process of multiplication. Multiplication can involve vectors in 3 different ways, all of which we need for this class, all of which are important and practical, all of which we need for navigating the physical world. Okay, 3 different ways that a vector can be involved in multiplication. One is a vector being multiplied by a scalar. One is a vector being multiplied by another vector in a manner that produces a scalar. And another way is a vector being multiplied by a vector in a manner that produces a vector. Okay, 3 different ways. The last one of them is the most complicated and the richest and the one we really ultimately need. But in order to play, and again, this is a totally different subject now. It's just other math that we need for this course is vectors. Okay, it has nothing to do, I mean, nothing directly to do with the cosines and all that. But in order to deal with vectors properly and all on the same page, I'm just going to make sure that let me establish my notation first. And the notation, at least for me, does make the concepts easier. So quick quick bit of vector notation here, at least the way it's used in physics. Like I say from now on, it assume, well, okay. And again, this is in one of those lectures, but wait, excuse me. I got a better idea. Hold on. Bear with me for 1 second. Feel free to ask questions too. Oh, or this is the moment that everything. No, okay. Just gonna do, sorry. Sorry. Have you, I mentioned this in the other class. I don't know if you guys know, there's this YouTuber named Gus Johnson that my 16-year-old son watches or used to watch. He's very funny. He's obnoxious. He's just like a dude, a YouTuber dude. I didn't even know about any of these YouTubers until my son, but there's this guy, Gus Johnson, who's just satirical and obnoxious, but he's got this one video where I forget what it's called, but where he makes fun of, how to be a professor in 3 easy steps or something. And he just savages professors for like an hour and a half, but he mostly savages how unbelievably incompetent and pathetic and awkward professors generally seem around technology and the web. And the video is hilarious. Like any competence I ever had with technology gets worse and worse now every time I'm in front of a class. And if I picture Gus Johnson at all, like he's hilarious and he's right. What I was going to do though, why I'm doing this is now at least I can do this right with you. Right, that's what I wanted to do. Okay. This is what I want to say about vector notation. Assume you've got some vector, i.e. some magnitude in some direction, and you call that vector A, right? And assume magnitude and direction matters, and that's like why we're using vectors. So assume we're in some context where we're paying attention to magnitudes and directions of quantities. So, and we want to know that. So we've got some vector called A, and assume we've got some other arbitrary vector, like a different length and a different direction, we call that B, okay? So assume that we put arrows over letters when we want to specifically designate that they are vectors, like that they have magnitude and direction. Like, of course, sometimes we don't care about that, but when we do, we put an arrow over a letter to mean that. And so then once we do that, we want to be very clear about distinguishing various parts of that vector. So I'm saying, assume we have vectors A and B. Then from here on in, we're going to say, then in such a context, if you just see the letter A written down without the arrow, then A specifically means the magnitude of the vector A, right? You see what I'm saying? Like sometimes if you just say A, it could mean in life. We don't know if it's a vector quantity or what. And if vectors are around, you just say A, we might assume it's not a vector quantity. If we know we're dealing with vectors and we've got some vector called A, then writing A down without its arrow is shorthand for the pure magnitude of A, and that I designate with double absolute value signs. Double because like absolute value means how far you are from 0 on a number line, right? But in vectors, we have more than a number line. We have multi-dimensions. So we expand the concept of absolute value to the concept of magnitude. It has a double sign to make that clear. So this means the pure magnitude of A. Similarly though, if similarly, we're going to now say, then let this symbol, now this, some of you may be very familiar with, this might be new to some of you. We're going to say from now on that A with a caret over it, a caret, which in physics we call a hat because we're pathetic. We literally read that as a hat, A with a hat over it. That is going to be called, that's a new kind of vector called a unit vector for A. Okay, so A with an arrow means the vector A. A with a hat over it means the unit vector A, or is read. It's read out loud as A hat. I know that's ridiculous. But what does it mean? What's the point of it? It's a piece of notation that specifically means this. A hat, given some vector A, then A hat necessarily means the vector A divided by the magnitude of A. Okay, sounds like we're going in a circle, but we got the vector A, it's got a direction and a magnitude. It's like an arrow, right, that points somewhere and has a length. I'm going to say from now on that if you take some vector A and you divide it by its own length, then you get a different vector that is called the unit vector for A. So, and it's useful and it seems stupid, but like, so you had this vector A, it had some length and it had some direction. If you make a new vector that's a lot shorter, or maybe it's even longer than it, but it's a different length, you make some new vector, well, it's a vector that will necessarily point in the same direction as A, but not be as long as it. In fact, if you take the vector A and you divide A by its own length, then the new vector you get, unit A, will necessarily point in the same direction as A, but it's scaled down by whatever length A had, so it's scaled down on purpose to a length of 1. In other words, A necessarily is defined to be a vector that points in same direction as A, but is defined to have a length of 1. It's a construct. It's an item that we establish for our own purpose. So if you have some random vector A, the unit vector for A is the vector that designates A's direction, but does it purely. It has necessarily a unit vector has a length of 1, so it's not conveying any other information in any distracting or corruptive way other than the direction of a certain vector. So in other words, it allows us, the purpose of this notation is it means that now this vector A that we had, some vector A, in the same way that we could talk about just its pure magnitude, its size, without getting bogged down in its direction, we can also now, using the unit vector, talk about its direction without getting bogged down in magnitude. And in other words, from now on, we can think of any vector A. All vectors in physics we think of as having magnitudes and directions, but we always tend to just say that in English, like, oh, don't worry. Like if you're on an exam and someone says solve for the velocity, they might have to remind you, like, that means get the speed and get the direction, right? It's always like this English after effect. But with this notation, we can literally now capture that. Any vector A is not just loosely, vaguely the combination of its own magnitude and its own direction, but in fact is literally a product. Any vector A can now be viewed as a monomial, a simple product of a pure magnitude times some pure direction. This is a way of isolating or distinguishing the different properties of a vector and being able to talk about them rigorously. A vector, what is some random vector? It's some random length pointing in some random direction. So how can we think of it? We can think of taking some vector that points in a particular direction, but only extends out 1 unit, in our coordinate system. And then, so we take some vector that points in a particular direction, call it A hat, and then you scale that vector up by a certain magnitude, call that A. And together, and by doing that, you have this whole package called the vector A. Okay, so from now on, a vector can be viewed as a simple monomial, a simple product of its magnitude by its direction. But with that notation, then that means all that direction component stuff we used to do in physics 1, like if you had to add displacements along 2 different axes, you had to divide them up into their components and add it. In other words, in physics 1, you used to say something like this: if you had some vector A, if in physics 1 or in mechanics you have some vector A, well, that's some length that's pointing in some direction, call it theta, right? and that's how we used to talk about it. We used to talk about some vector, whether it's displacement or velocity or acceleration. You picture some vector A, you could picture it as an arrow of some length going in some direction. What I'm saying now is, yeah, it's an arrow of length A going in a direction of A hat. A hat is conveying the same information as theta, right? We could say that now, and that's very convenient. But what's not convenient, or why we're not done, is that of any vector can be viewed as its pure magnitude times its pure direction. But its direction may not be convenient in any way if you're trying to relate one vector to another. Remember, for example, if we have a vector A and a vector B, two different vectors, they can both be written the way I'm writing. But now each vector is written as a pure magnitude times some direction that's only interesting to itself. Like the direction of each of these vectors doesn't have anything to do with the other vector, right? So what we like to do is find directions that are convenient to everything in a situation. That is, we like looking at vectors in coordinate systems, whether they be like XY coordinate systems or what. And just like we like dividing, if you have to take a set of directions and navigate somewhere in Manhattan, in New York City, we like to divide up directions in our mind into blocks and avenues, like north-south components and east-west components. Well, same thing here. All directions are equivalently usable, but some are more convenient than others. So what we tended to get into this habit in physics 1 is, instead of saying that a vector is its own direction times its own magnitude, we would say, you know, this direction of A is not in and of itself terribly convenient, but the x-axis and the y-axis, we can use an x-axis and y-axis to discuss vector A and vector B in the same coordinate system and relate them to each other. In other words, what we used to do last year is we would, I think, or what you used to do in some prior physics courses, you would say something like, if we had this vector A, any vector could be thought of as the sum of two smaller tip-to-tail vectors, that each of which pointed in some direction that was more convenient. And that's all, just more, not more accurate, but just more convenient. In other words, we could say something like, we could say that the vector A is the tip-to-tail sum of its components, the vector AX plus the vector AY. And what does that mean that it's equal to the sum? Like, we don't mean number-wise, we don't mean arithmetically. Like, for example, if this width happened to be 3 and this height happened to be 4, we're saying that the length of this final vector is 5. I don't think 3 plus 4 equals 5 arithmetically. I do think 3 plus 4 equals 5 vectorially, meaning I do think that in New York City, if I walked 3 blocks due east and then I walked exactly 4 blocks due north, I think it is fair that if you then measure what I did at the end of the day, my ultimate displacement will have been 5 blocks to the northeast at some angle, right? I mean, that's, to add vectors means to take into account direction. So any one overall vector A can be thought of as the sum of its constituent more convenient vectors AX and AY. And what are each of them? Each of them is some magnitude, like how far something brings you along an X. Yeah, each one of them could be written like this, right? So I'm saying, on the one hand, a vector can be viewed as a simple monomial, a simple product of its pure direction and its pure magnitude. That is a true statement. But it's also true that any vector can be viewed as the sum of smaller vectors, just like any number on the number line. The number 7 can be viewed as 3 plus 4. So any vector can be viewed as a product or it could be viewed as a sum. It's convenient to view vectors as sum of smaller vectors. It's convenient because we then, by those smaller vectors, we mean component vectors that lie along axes that we've already agreed upon to be convenient. So any general vector A can be viewed as the sum of its smaller X and Y vectors, right? But still with the notation, like each one of those vectors is a pure, each one of those constituent vectors is a pure magnitude times a pure direction, and we're almost done with this. So just to continue, and again, this, well, I'm saying therefore any arbitrary vector A could be understood to be the sum of smaller vectors. In fact, specifically, oops, sorry. You could do this in three-dimensional space, with which we're really concerned in physics. Right, so this says AX times X hat plus AY times Y hat plus AZ times Z hat. It's just using the, right? Each one big vector is the sum of three component vectors, each of which is a pure direction, a pure magnitude lying along some axis. And each one of these component vectors will only lie along that axis, no others. That's sort of the point of this. And finally, so X hat just means, you know, a vector that has magnitude 1 but lies along the X axis, etc., with Y hat, etc., with Z hat. Because the X and Y and Z axis come up so often, there are convenient axes that we choose, you know, however we rotate them, we choose these three axes to fit all of our problems into, because they're meant to accommodate more than one vector at once. And because X, Y, and Z come up so much in all of our notation, and it can get so confusing, we actually give special names to those three unit vectors. Okay, so let me say again, I'm saying anything, if A is a vector, right? If A is a vector, then A hat literally means that the vector A divided by its own length. If B is a vector, then B hat is the vector B divided by its own length. So anything that you put a hat over it, you're talking about the pure length, I'm sorry, the pure direction of that vector. So if a vector happens to lie along what you're calling a coordinate axis, that's so kind of convenient and important and special and thick in notation that we say, let, from here on in, let any unit vector pointing along the x-axis, we're from now on going to call the unit vector I. This is an I. Oh, this is confusing. And we're almost done, I know, but definitely got to catch this. I'm about to introduce something called I. I don't mean the lowercase I that we were just using for imaginary numbers 20 minutes ago. It's a weird coincidence for two I's to come up in a physics class like this, but this is a totally different I. How can you tell the difference? And the two contexts will never meet. Don't worry about the two contexts meeting and confusing things. But the I that I'm talking about now is the lowercase letter I in the alphabet that you'll never see me use unless I put a caret over it. Like I'm saying the unit vector from now on that lies along the x-axis isn't called x hat. I mean, some people do call it that, but most people don't. Instead of calling it x hat, we're going to call it I hat. And similarly, the unit vector, similarly, the unit vector that lies along the y-axis is called j hat. And the unit vector that lies along the z-axis is from now on called k hat. That's how I do a lowercase k. That's my lowercase j. Again, for x, my lowercase I looks like a J backwards, like it just looks that way. But I'm putting a hat over each one. This is just notation now. And many of you have never seen a unit vector at all. So I'm saying two things. I'm saying there's unit vectors from now on. Any given vector you have, if you want to just talk about its pure direction, if you want to talk about how it's oriented, then you think of a little vector that designates its orientation, but only has a length of 1. So it doesn't screw up multiplication and stuff. We'll call that a unit vector. But I'm also saying in the same breath that from now on, the unit vectors that correspond to our Cartesian axes, they have their own special names. They are I, J, and K. Okay, so from now on, however you think of vectors, if you think of them as arrows that have size and direction, which is a pretty good way to think of them, then from now on, some random vector A can really be thought of as a sum of its x, y, and z components, right? And the way to write that in one fell swoop, sorry, I'll just do it on the next page. The way to write that on one fell swoop is if some given three-dimensional space, and given the vector A, then it will always be fair and true to say that A can be written down, broken down, understood as some amount, some scaling factor times an amount that is pointed along the x-axis plus some amount along the y-axis plus some amount along the z-axis. This is a more complicated looking way to write a given vector, to write it as a polynomial, as the sum of products. But what that really means is it's the tip to tail composition of a bunch of simple directionals that lie along convenient unit axes, sum of products. Sum of products. So from now on, vector A looks like that. And then similarly, you know, if you have some vector V, then B is going to be its some amount in the x-axis, like this. And notice every time I write like B sub x or B sub z, that just refers to a number. It refers to the pure length of the component of the B vector that lies along that particular axis. Now, this is just notation. I haven't taught anything. I'm not, maybe by accident, hopefully, but I'm just saying this is how I think about vectors. I think of them as arrows that are composed of smaller arrows, and I could separate their direction and their size in my mind by means of this unit vector notation. So again, like from now on, if the vector is A, then A is defined to be the vector divided by its own length, such that any vector A is its own length times the unit vector. Like, now given that, what's that got to do with multiplying? Well, okay, back to multiplication, and then we're going to be. You can take some vector, form way number one of doing multiplication in a way that involves vectors. The first way you can is what we've been using this whole time. You can take some vector and multiply it by a scalar. That just means you take some arrow and you multiply it by a quantity. It means you take some arrow and you make it bigger or you make it smaller. That quantity we call a scalar for just that reason. If you multiply a vector by a pure magnitude, you're scaling up the arrow or you're scaling it down, right? In other words, like the first kind of vector multiplication is just taking some vector A, taking some vector A and multiply it. Yeah, let's even be, sorry. Just assume if we said that A stood for some vector and we could say for example, let lowercase number, we'll use lowercase letters to stand for scalars, let B equal some pure scalar quantity. In other words, just a pure number. Then the first form of multiplication that ever comes up, the multiplication form number one, is taking some vector A, multiplying it by some scalar B, and that equals just exactly what you think. It just equals all the parts of that vector being scaled up. It equals just what you think. To multiply a vector, in other words, if you multiply a vector by a scalar, what you definitely get is still a vector. If you multiply a vector by a scalar, you still get a vector, and we've been relying on that to construct all these bigger vectors out of smaller vectors in the first place. That's just, right, it's just a constant. Yeah, just a constant, yes. The B is just a constant, and specifically with no direction, that's right. So scalar multiplication almost doesn't seem interesting. We've sort of been taking it for granted the whole time, but it does turn out to be important. It's how electrical field, multiplying a vector by a scalar seems silly, but it's actually the essence of an electrical field. We'll get to that. But now what's more related to this homework and the more exotic thing is, say you have two vectors and you want to multiply them by each other, like what happens? Do you get a vector or do you get a scalar or how or what? And the answer is either one can happen. It's your choice. If you want to multiply two vectors together, there's two ways to do it, two different tools. Each one works all the time. Like any given two vectors you can imagine, you can multiply them in either one of two following ways, and you make a choice depending on what kind of thing you're looking for, like what the physical context is. Both things will always be right. It's just a question which is relevant. So multiplication form number 2 is scalar multiplication of vectors So you take two vectors and multiply them in a fashion that produces a scalar. Assume that that's a circumstance. I mean, you might ask, why would I ever want that? But you could just as easily ask, why would I ever want to multiply two vectors and produce a vector? And we're going to answer both. So these are just the two tools for any circumstance that could arise. And of course, we'll look at the circumstances. But scalar multiplication of two vectors means that you want to multiply, you want to measure a relationship between the two vectors. You want to somehow account for these two vectors in a manner that does not incorporate, focus on, or emphasize direction, right? If you want some operation that allows you to multiply two vectors and return a non-vector, it means somehow you want to multiply two vectors and return something that doesn't have a direction. It means you want to look at them in a manner that somehow allows you to drop the whole issue of direction in the end. How could that possibly be? Well, the way this works is this form of multiplication, this form of measurement, this measures the relation between two vectors, or sorry, measures a relation between two vectors which de-emphasizes direction. I apologize for this. So what that really means is this operation is a form of multiplication that allows you to take two vectors and spit out an answer that lies on a regular old number line. In other words, this operation will return bigger and bigger values the more it is true that the two vectors behave as though they were just on a number line. In other words, what I'm saying is, I'm saying if there's some operation that allows us to measure a relationship between two vectors, and if it allows us to spit out an answer that doesn't have any direction in it, in other words, well then, if that's the case, it better, whatever answer this operation spits out, it better spit out the same answer that regular old everyday multiplication would spit out if the two vectors happen to both lie on the same number line. In other words, whatever scalar multiplication of two vectors is, whatever it is, however it works, whatever I need it for, say I have a vector that's length 3, and I have another vector that's length 2. I don't know exactly how to multiply those two vectors together, but if there's a way to multiply them together and get just a simple answer, I'm going to say the answer better be 6 if those two vectors happen to be parallel. If those two vectors are pointing in the exact same direction, then then they're both pointing along the same axis. And then a vector of length 3 and a vector of length 2 are just, if they're both pointing on the same axis, then they're just like then they're just the number 2 and the number 3 multiplied by each other, and I get the number 6, right? In other words, this form of multiplication, scalar multiplication, better look more and more like regular everyday multiplication the closer and closer the two vectors are to being unidirectional, to being parallel to each other. Scalar multiplication of two vectors is ultimately a measurement of how parallel two vectors are, how aligned they are. The more aligned they are, the bigger their scalar product will be. Specifically, this product we end up calling the dot product, and we say this form, the dot product it's called dot product just because we use a dot to designate it, but specifically that's shorthand for the scalar product of two vectors is going to be the length of one vector times the length of the other vector times the cosine of whatever acute first quadrant angle is between the two of them if you draw them tail to tail. So if your two vectors are like, here's A and here's vector B, right? And they're different directions and different lengths. The scalar product of these two vectors is a number which is bigger, which gets bigger and bigger if either or both of these two vectors get bigger and bigger. It's like a vector of length 3 times a vector of length 2 in this fashion will, produce something, but a vector of length 3 and an identical vector of length 7 will produce an even bigger product. But the cosine factor is saying if theta is the angle between them, well, the cosine of 0 is 1. The cosine of 90 degrees is 0. So the dot product says take the bigger each vector is, the bigger your overall answer is going to be, but also the more parallel to each other these vectors are, the bigger your whole answer is going to be. If they're literally parallel, if theta is 0, then cosine of theta is 1. And then the dot product of A and B will literally be what you'd expect, the numerical arithmetic product of A and B. Because if theta is 0, it's as though you have two vectors, just two arrows along the same axis, i.e. just two different places on the number line, two numbers. But as theta gets bigger and bigger, as it gets closer and closer to 90 degrees, as the two vectors start to differ from each other more and more directionally, then it's less and less fair to reduce this to a simple number line operation. So the length of one could be 17 and the length of the other could be 29. But if they're just about perpendicular with each other, then that cosine is going to be almost 0 and their whole dot product is going to be 0. So the scalar product measures parallelism in effect. And the classic example you had in physics, the classic example where a dot product is worthwhile is that work, a little bit of work, strictly speaking, is defined to be force times a little bit of displacement, right? Work is force times displacement, but displacement is a vector and force is a vector. So truly, specifically, what work really is some kind of product of these two vectors. Work, from physics 1, work happens to be the most vivid example of a dot product between two vectors, because what it's really saying is that you don't just multiply any random force times any displacement to see how much energy is being transferred. Only a force that's relevant to some displacement or contributing to it will transfer energy. In other words, if I'm going like this with my pen, I'm pushing my pen horizontally across the video screen. I'm pushing my pen across. So the force of friction from my hand, friction from my hand is exerting a force horizontally on the pen, static friction, and the pen is displacing. So the friction from my hand is doing some work on this pen, displacing it horizontally. But while this is happening, there's also the force of gravity pulling down on the pen. The pen has weight. Weight is pulling down, without a doubt. That's a force in the free body diagram. But the pen is displacing horizontally. Well, there is a force and there is a displacement. but the angle between them is 90 degrees. The force doesn't have anything to do with the displacement. It's not because of gravity in any way that the pen is sliding horizontally, and I see the time. And gravity is not, therefore, transferring any energy to the pen as it does this. So whenever we say, so that's an example of this, we say that work is a dot product of force vector with displacement vector because it's only the alignment between the two vectors that should be contributing to the final quantity. Okay. Lastly, I'm going to end on, I know class is over now. You know, this is the intro to the dot product. I haven't explained the cross product yet, although I did define it, you know, which is knowing the definition, you can do all the homework, but I'm trying to make sense of it now. I'll just say this, you might want to practice this when you leave, or if you still haven't finished homework 2, like, given all that I said, ask yourself, what is the unit vector I dotted with, we'll probably start from here next class, but what is I hat dot I hat? There is an answer. Like, what is I hat dot J hat? There is an answer, and the answer is always the same. If you understand what I'm saying about these vectors, you'll know. Like, I hat dot with I hat is something. I hat dot with J hat is something. And even like K dot J is something. And so is negative K, for example. All these things have meaning, and we'll get to the cross product next class, but blah, blah, blah. I will post the new homework soon. I will get you back your homework soon. If you've done everything so far and you don't see a homework 4 posted yet, then there's nothing you can do yet until it gets posted, so congratulations, that's good. Is it I plus theta? Is it I? No, it's not I cosine. It just has a question. It's cos theta plus I sine theta. There's no I before the cos, but don't stress about that too much. Okay, I think I'm holding you up from lab, at least half of you. I think we all should go. I will start talking more about office hours and things like that. But everybody's doing great so far. I think, I'm sorry, I didn't get a lot of, I hope everything's clear today because there have been a lot of questions. We'll talk less tomorrow. I will stop talking now. I'm gonna hop off immediately so that you can go and so I don't cause confusion. But you are wonderful people. May the net force be with you. And go H Bomber guy. I love that guy. H Bomber, great guy. All right, bye.